In this video, we're going to take a look at matrices and matrix operations. So a matrix is a rectangular array of numbers, and remember rectangle includes squares, of numbers with m rows and n columns, and this is how we denote the size. So notice in my picture here where I don't have any real elements, I've got 3 rows and I've got 2 columns. So things to understand about matrices is that the address of each element, so each of the items inside the matrix is called an element. The address of each item inside of the matrix, for instance, M11, tells me that this value is in the first row, first column. So you can see, looking at M32, that is third row, second column. So it's always rows by columns. So let's say I had a matrix 0, 1, 0, 2, 4, 5, and we're calling this matrix N. So we might be asked to determine the dimensions, and the dimensions here would be a 2 by 3. 2 by 3 because I have 2 rows and 3 separate columns. If I wanted n 2, 3, what would that value be? So n 2, 3 means an element in matrix N, and this says my second row, so I'm looking at this row, and this says my third column, and so that value is 5. So again, this would be called the address, and this is the value of the element. So we're going to talk about a couple of different matrix operations, and the first is matrix addition, which is basically the same as subtraction. As we know, it's the same concept. So I'm going to make up just a couple of matrices here, and I'm going to let A be 1, 2, 3, 4. This is a 2 by 2 matrix. I'm going to let B be 4, 5, 6, 7, and I'm going to let C be 7, 8, 9, 10, 11, 12. And so what we know about matrix addition and subtraction is that they have to be the same size, and by the same size we mean the same dimensions. So we know A is obviously a 2 by 2 matrix, and B is a 2 by 2 matrix, and C is a 2 by 3 matrix. So right away I know that this is not going to work to add or subtract with A or B. However, if I were asked to find A plus B, I could do that very easily, and I'm going to rewrite just for the sake of ease here. So I'm adding these values together, and essentially all I need to do, and this is why they have to be the same size, is I'm just going to take the first column, first row, and add those two elements together. So I'm adding corresponding elements together. So 1 plus 4 is 5, and then I'm going to add 2 plus 5, and it doesn't matter the order that I add these. Then I'm going to add 3 plus 6, and then I'm going to add 4 plus 7, and that's how we do addition. Subtraction, obviously very similar. I'm still just going to do a rewrite. Oops. 4, 5, 6, 7. And it's up to you if you want to just straight up subtract. 1 minus 4 obviously gives me -3. With some of my other classes who have a hard time with subtracting and negatives or get them confused in their heads, you can always change that minus to a plus and change the sign of everything inside, and that's really up to you whether you want to subtract or add the opposite. So 1 plus -4 is -3, 2 plus -5 is -3, 3 plus -6 is -3, 4 plus -7 is -3. So matrix multiplication is a little bit more involved, a little bit more difficult. And the most important thing to understand is that you cannot always multiply two matrices together. So if I look at my explanation here, I say that I can multiply them if m is m by k and n is k by n. And essentially what I'm saying is the number of columns of my first matrix has to be the same as the number of rows of my second matrix. And otherwise it's not going to work. If it does work, my resulting matrix is m by n. So let's take a look at if we can take a times b and if we can take b times a. So looking at a times b, a is a 2 by 2, b is a 2 by 3, and what I see here is 2 is the same as 2, so I know that I can multiply. So I'm going to go ahead and multiply this out. I'm going to recopy matrix A. I'm going to leave myself some space, and you'll see why in a little bit, and I'm going to rewrite matrix B. I know that my resulting matrix is going to be 2 by 3, so I'm going to leave myself space for my 2 by 3 and then go from there. So as I'm multiplying this, essentially what I want to do is I want to take this row by these columns. So when I take row 1 times column 1, I should get my solution for row 1, column 1. So what I tell students to do, and again this is up to you, is it might be easier to take this and kind of write it in a vertical fashion instead, because what I'm going to be doing is I'm going to take 1 times 4, or negative 1 times 4, which is negative 4, and I'm going to take 3 times 5, which is 15, and I'm going to add those values together, because now I've taken row 1 by all of column 1. And then I'm going to take negative 1 times 3, which is negative 3, and I'm going to take 3 times negative 1, which is negative 3. I'm going to add those together. I'm going to take negative 1 times negative 2, which is 2, plus 3 times 0, which is 0, and I'm going to add those together. And I'll do that in just a little bit, but before I do that, I'm going to go ahead and do my second row. So now I'm taking 4, negative 2, and I'm going to do the same thing and then put it on that second row. So 4 times 4 is 16. Negative 2 times 5 is negative 10. 4 times 3 is 12. Negative 2 times negative 1 is 2. 4 times negative 2 is negative 8. Negative 2 times 0 is 0. My final solution is just all of those sums. So I've got negative 4 plus 15, which is 11, negative 3 plus negative 3, which is negative 6, 2 plus 0, which is 2. On the bottom, 16 plus negative 10 is 6, 12 plus 2 is 14, and negative 8 plus 0 is negative 8. So that is how we do matrix multiplication. Let's take a look at B times A. Remember, B is a 2 by 3 matrix and A is a 2 by 2 matrix, and if I check the dimensions here, I can see that this is not possible. You need those dimensions to match up. So let me show you why that would not be possible. Again, using the same process we just had, if I try to multiply this row, and I use that same strategy where I kind of rewrite it, 4, 3, negative 2, notice it doesn't line up. I need to have it correspond correctly. So here are some questions for us to try, and we're just going to work through these together. But if you'd like to, you can certainly press pause, try all 6 of these questions, and then press play to see how you did. So I have 2 matrices here, A is obviously a 2 by 3 matrix, and B is a 2 by 2 matrix, and I'm asked to find a lot of different things. So first I'm asked to find A minus B, but what we know about subtraction is that these dimensions would have to be exactly the same, so I'm just going to put NP for not possible. Then I'm asked to find A times B, and A times B would mean I'm taking a 2 by 3 times a 2 by 2, and again, those don't match up, so that's not possible. Then I'm looking at B times A, so I would be taking a 2 by 2 by a 2 by 3, and because these dimensions do work, it is possible. So I'm going to go ahead and steal some of that real estate from my previous question, rewrite B times, and again I'm going to leave myself some space, times A, which is 0, 1, negative 1, 4, negative 7, 3. In order to multiply, I'm going to take my negative 2 and 8 and sort of make it a column. So my solution here would be negative 2 times 0, which is 0, plus 8 times 4, and then negative 2 times 1, plus 8 times negative 7, and then negative 2 times negative 1, plus 8 times 3. And again, I could have done this ahead of time to make sure I remember that I've got a 2 by 3. Then I've got my new column. So I have 7 and 6. So 7 times 0 is 0. 6 times 4. 7 times 1 is 7. 6 times negative 7. 7 times negative 1, and 6 times 3. And then my final answer is just finding all of those solutions. So I have 32, negative 58, 26, 24, negative 35, and I can't read my own writing, that's an 18. Okay, so 11. And that would be my final solution. Now let's look at A squared. So we haven't really talked about what happens when we square. So some people would take A and say 0 squared is 0, and 1 squared is 1, and negative 1 squared is 1, and 4 squared is 16, and 49 and 9, and there you go. And that is absolutely not the case. We can't do that. So what we can do is we can look at the fact that A is a 2 by 3 and A is a 2 by 3, and we can see that we cannot take these matrices times one another, and so this is not possible. Looking at B squared, however, this is a 2 by 2 times a 2 by 2. And this one is possible, and so I would actually just write this twice, negative 2, 8, 7, 6, negative 2, 8, 7, 6, and I fear I have not left myself enough room here, but we're just going to go for it. So remember, you can take negative 2 and 8 and put it this way. So I've got negative 2 times negative 2, which is 2. I'm sorry, which is 4, and 8 times 7, which is 56. I've got negative 2 times 8, which is negative 16, and 8 times 6, which is 48. I've got a new row, 7 and 6, to give me negative 14 plus 42, and then 7 times 8, 56, plus 6 times 6, 36. So my final solution here, if I can read my horrible handwriting, I've got 60 for my first term. I think that's a 48. That would give me 32. Negative 14 plus 42 gives me 28. And 56 plus 36 is 92. So there is my solution. 2b, which is sort of something we haven't really talked about before, but honestly it's pretty straightforward. And basically this is called scalar multiplication. So I'm taking b and I'm just doubling all of the terms, and that's all I'm doing. So that would give me negative 4, 16, so it's essentially like me distributing 2 times 7, 2 times 6, and that would be my new solution. I have two other concepts that I want to talk to you about, and the first is the identity matrix. And I'm going to try to get through this quickly because I know we took our time on the other questions. So the identity matrix essentially says if I take a matrix and I multiply it by the identity, I should end up back at the matrix I started with, and we're going to do one of these examples together. And the identity matrix is a square matrix, and again all of this stuff in yellow is the official definition, and that basically says that if the address of the row and column are the same, the value is a 1, and if they're not, then the value is a 0. But basically it's just the first diagonal is 1s and everything else is 0. So let's take a look at A. And I didn't make this clear before, but notice in all of my matrices I'm using brackets, and that is what you should use. We will talk more later about finding the inverse, etc., or the determinant, and we might use some different brackets then. The identity matrix for a 3 by 3 matrix is 1 0 0 0 1 0 0 0 1. As we can see, that's that first column I was talking about. So let's take a look at what happens when I multiply them. I'm going to take 2 1 3 and I'm going to multiply, and I know I'm going to end up with a 3 by 3 matrix. 2 times 1 gives me 2, and notice the other two values are going to be zeros, so it's just 2. And then 2 times 0, 1 times 1 gives me 1 plus 0. And then 2 times 0, 1 times 0, 3 times 1 gives me 3. And notice right away that 213 is still 213 even after multiplication. Then I'm going to take 4, negative 2, 7. I'm going to do the same thing. It's going to give me 4 plus 0 plus 0, 0 plus negative 2 plus 0, and 0 plus 0 plus 7. And my last one, 0, 1, negative 1. Sorry, I meant to use a different color there. 0, 1, negative 1. Then I'm going to end up with 0 plus 0 plus 0, 0 plus 1 plus 0, and 0 plus 0 plus negative 1. So we can see that in fact we do have the exact same matrix that we started with before. The last concept I want to talk to you about in this video is the transpose of matrices. And we can see that the transpose basically takes an m by n matrix and turns it into an n by m matrix. Should have used different letters there so they didn't sound the same. So let's say A is a 2 by 3 matrix. So 4, 5, 7, 0, 1, negative 1. The transpose of A would be taking my first row and instead making it my first column, and taking my second row and instead making it my second column. So we can see that the transpose of A is not the same as A, therefore they are not symmetric, because if they are the same we consider them symmetric. So let's take a look at one that it would be symmetric. Let's say A was instead 1 0 0 1. Then the transpose of A would be taking 1 0 and making it a column, and 0 1 and making it a column, and we can see that these two things are equal and therefore they would be symmetric. Now that you know how to perform matrix operations by hand, let's talk about how we can simplify the process by using your TI-84 calculator.